Networks don't slow down by accident. You know that feeling, right? Smooth connections suddenly freeze, throughput drops, latency spikes. It feels random, but it's not. There's a hidden logic behind every slowdown. And once you understand it, the entire network just makes sense. We're going to uncover that logic using two foundational models, the network path model and the network congestion model. By the end of this course, you won't see congestion as a mystery anymore. You'll see it as a pattern you can recognize instantly in Wireshark. Packets tell the secrets. Wireshark listens. And you see the truth. I'm Tai Fung, and welcome to my network analysis class. Let's dive into our first core concept, the network path model, where we learn that every path is really just one pipe. Imagine water flowing from a wide pipe into a narrower one. When the water hits that narrow section, it can't pass through as quickly, so it starts to slow down and accumulate. Well, a very similar thing happens in computer networks. Data packets often move from a high-speed link into a slower link somewhere along the path. When packets arrive faster than the outgoing link can transmit them, the excess packets begin to pile up. Now, if nothing was done, those extra packets would just be dropped immediately. To prevent that, network devices like routers include something called buffers. Think of a buffer as a temporary storage area, a small reservoir placed between that wide pipe and the narrow one. When the outgoing link is busy, the buffer holds those extra packets until the link frees up. This gives the system some flexibility and stops short bursts of traffic from causing instant packet loss. But here's the catch. Buffers are not unlimited. If traffic keeps arriving faster than the link can transmit for too long, the buffer will eventually fill up. And once it's full, newly arriving packets must be dropped. This leads to a crucial observation. The slowest link along the path ultimately determines the maximum throughput of the entire path. No matter how fast the earlier links are, traffic must eventually slow down to match that slowest segment. Buffers help smooth out temporary mismatches, sure, but they cannot eliminate the underlying capacity limit. So in short, speed mismatches create congestion. Buffers provide temporary absorption, and once buffers fill up, packets get dropped. Now let's shift perspective to the second part of our model. The network path model through TCP's eyes. A real network path might have dozens of routers, links, and different speeds. But TCP doesn't need to understand all that internal complexity. Instead, TCP effectively treats the entire path as a single pipe. For any single TCP connection, there is typically one slowest point along the path in each direction. We call this point the bottleneck. This bottleneck determines the maximum rate data can be delivered, and it's exactly where packets begin to queue when congestion occurs. From TCP's point of view, we can simplify the entire network path into a pipe, characterized by just three essential parameters. First, bottleneck bandwidth. Second, base round-trip time, or base RTT. And third, buffer capacity. These three values define the fundamental behavior of the path. Let's break those down. First, bottleneck bandwidth. This represents the maximum data rate packets can pass through that slowest link. But for a specific TCP connection, what really matters isn't necessarily the theoretical link capacity, but the share of bandwidth actually available to that flow. This could be naturally unused capacity, or it could be limits imposed by policies like QoS. This value determines the maximum achievable delivery rate. Second, base RTT. This is the minimum possible round-trip time between sender and receiver when there is no queuing delay. It represents the pure propagation and processing delay, the intrinsic latency of the path. Third, buffer capacity. This is how much data the bottleneck device can temporarily hold when incoming traffic exceeds the outgoing rate. Whenever packets arrive faster than the bottleneck can transmit, a queue forms. As the queue grows, packets experience more delay. And once the buffer is full, any new packets are dropped. Although, in strict policing scenarios, they might be dropped immediately without queuing. From these three fundamental parameters, we can derive two important values that help us understand TCP behavior. The first is the bandwidth delay product, or BDP. If we multiply the bottleneck bandwidth by the base RTT, we get the BDP. Let me write that out clearly. BDP equals bottleneck bandwidth multiplied by base RTT. This value represents the amount of data required to fully occupy the pipe when no queuing occurs. If your data in flight is less than the BDP, the pipe isn't fully utilized. If it approaches the BDP, the link becomes fully utilized. Here's a quick example. Say your base RTT is 10 milliseconds and your bottleneck bandwidth is 100 megabits per second. To calculate the BDP, we convert 10 milliseconds to 0.01 seconds. Then 0.01 times 100 million bits equals 1 million bits, or 125,000 bytes. This means you need approximately 125 kilobytes of in-flight data to fully utilize that path under ideal conditions. The second derived quantity is the total in-flight capacity. This is simply the sum of BDP plus the buffer size. This represents the maximum amount of data that can exist inside the network path before packet loss begins, assuming a traditional tail drop queue. Conceptually, the BDP fills the propagation portion of the pipe, while the buffer capacity holds the extra data when incoming rates exceed outgoing rates. Together, they define the upper bound on total data in flight. If you exceed this limit, packets will start dropping. Now, another important characteristic is how the bottleneck device manages its queue. Different devices use different strategies. Queuing policies define how packets are scheduled. Examples include FIFO, priority queuing, or fair queuing. Drop policies define how packets are dropped during congestion. Common examples are tail drop, where packets drop only when full, red or random early detection, WRED, and CODEL. These mechanisms influence how congestion signals are generated, which in turn affects how TCP adjusts its sending rate. So to summarize this section, from TCP's simplified view, a complex network path becomes a single abstract pipe defined by bottleneck bandwidth, base RTT, buffer capacity, and queuing behavior. All the underlying complexity disappears inside this abstraction. TCP doesn't see routers or links. TCP sees a pipe, and every congestion event originates from the bottleneck of that pipe. Next, let's zoom out to look at the complete picture, the TCP end-to-end path. In end-to-end transmission, performance isn't just influenced by the network itself. It's also constrained by limits at both the sender and the receiver. So a TCP connection is constrained by three types of limits: sender-side limits, receiver-side limits, and network path limits. Together, they determine how much data can exist in flight at any moment. On the sender side, two factors matter. First, CWND, the congestion window. This is maintained by TCP's congestion control algorithm. It determines how much data the sender believes the network can handle without causing congestion. For example, if CWND is 100 kilobytes, TCP won't send more than that amount of unacknowledged data, even if the network could handle more. TCP intentionally restrains itself to avoid overloading the network. The second factor is the send buffer size. This is the amount of data the sender is willing to buffer. Even if the algorithm allows a large CWND, the sender can't transmit more data than it actually has buffered. Imagine CWND is 100 KB, but the send buffer is only 64 KB. In this case, the sender simply doesn't have enough data to utilize the full window. So while the send buffer doesn't determine CWND, it can limit how much data is actually in flight. It's an invisible but very real limit you should never ignore in Wireshark. On the receiver side, flow control is key. The receiver advertises its receive window, or RWND, in TCP ACK packets. It's basically telling the sender, this is how much free space I currently have. The sender must respect this limit. The receive buffer size determines the maximum possible receive window, meaning RWND is always less than or equal to the receive buffer. If the buffer fills up, the receiver reduces RWND, forcing the sender to slow down. This is TCP flow control in action. Between the sender and receiver lies the network path we discussed earlier, with its bottleneck bandwidth, base RTT, and buffer size. As we said, the network places an upper bound on data in flight, roughly equal to BDP plus the bottleneck buffer. Now, if we list all possible limits, we get a formula. Bytes in flight is less than or equal to the minimum of send buffer, CWND, receive buffer size, RWND, and BDP plus bottleneck buffer. But wait, one of these is redundant. The receiver doesn't directly expose its buffer size, it advertises available space via RWND. Since the sender must obey RWND, the receive buffer constraint is already covered. On the sender side, however, CWND and send buffer are different constraints. CWND limits what TCP allows to be sent. The send buffer limits what data is actually available. After removing the redundancy, we arrive at the simplified model. Bytes in flight is less than or equal to the minimum of four things: send buffer, congestion window, CWND, receive window, RWND, and network queue capacity, which is approximately BDP plus bottleneck buffer. These four limits act like valves along the end-to-end TCP path. In real networks, especially under traffic contention, these valves are dynamic. At any moment, one is always the smallest. While the specific constraint may shift over time, a minimum limit always exists. This smallest limit becomes the active constraint, determining the maximum bytes in flight. Therefore, in performance troubleshooting, our primary task is to identify this limiting valve. We can now understand pipe utilization using two critical watermarks, BDP and BDP plus buffer size. When bytes in flight is less than BDP, the pipe isn't fully utilized. When it equals BDP, the pipe is full. When it exceeds BDP, additional packets accumulate in the bottleneck buffer, forming a queue. Bytes in flight can keep growing until it reaches approximately BDP plus bottleneck buffer. At that point, further packets will likely be dropped. But the story doesn't end there. Those four valves define the theoretical limits. They set the ceiling. But ceilings alone don't determine behavior. This brings us to the fifth and perhaps most dynamic factor: feedback signals, because TCP is fundamentally a control loop. The sender is blind. It doesn't know the true capacity of the path. It relies on its congestion control algorithm to learn about the network through signals returned by the receiver. The only thing it sees is what comes back in the form of ACK packets. As packets travel the path, they experience errors like random loss or reordering. They experience queuing and drops. Under tail drop, packets drop only when the buffer is full. But with mechanisms like RED, packets drop before the buffer is full. This means the actual bytes in flight may never reach that theoretical ceiling because early drop policies trigger loss sooner. Also, receiver-side processing matters. Delays, delayed ACKs, or offload features can impact things. And don't forget the return path. ACKs are impacted by network conditions on the reverse path, which might be totally different from the forward path. Ultimately, the sender learns about all of this only through the ACKs it receives. We can group these feedback signals into three types. First, loss signals. These are hard signals like the sound of metal fracturing. They include duplicate ACKs, timeouts, and ECN marks. In traditional algorithms, these signals force TCP to reduce CWND abruptly. They define the lower boundary of stability. Second, timing signals. These are softer, like the deformation of a pipe under pressure. They are early warnings. Before a system collapses, pressure builds. Timing signals reveal queue buildup before packet loss occurs. Examples include RTT increase, RTT jitter, and ACK spacing variation. When RTT increases, queues are forming. When jitter increases, the queue is unstable. Modern algorithms like BBR rely heavily on these timing signals to estimate bandwidth and operate right at the edge of full utilization without triggering loss. Third, ACK behavior signals. This is the flow rhythm. TCP is ACK clocked. The pattern of ACK arrival determines how data is sent. This includes regular pacing, reordering, compression, starvation, or delayed ACKs. They are like the rhythm of a heartbeat. Even if the forward path is stable, distortion in the ACK stream can change send behavior. For instance, ACK compression can cause burst transmission, while ACK starvation can stall growth. In one word, the pattern of ACK arrivals shapes the sender's transition behavior. TCP doesn't send when it wants to, it sends when it's allowed to. And permission comes in the form of ACKs. Here is the key insight. The four valves define the theoretical ceiling, but feedback signals determine how close TCP can actually operate to that ceiling. Loss sets the hard boundary. Timing signals reveal pressure buildup. ACK behavior shapes transmission dynamics. They tell the sender to speed up, slow down, or retransmit. Actual BIF is not determined by limits alone. The valves define capacity, but feedback signals define behavior. And in real networks, behavior often matters more than theory. So from an end-to-end TCP perspective, actual BIF is determined by two layers: system limits, which are the 4 valves capping the maximum bytes in flight, and control feedback, the signals guiding congestion control decisions. TCP behaves like a closed-loop control system, a blind sender, plus network feedback, plus continuous adaptation. The limits define the ceiling. The feedback defines reality. Finally, let's expand our view one last time to the application end-to-end path. So far, we've built a complete model of the TCP pipe. We understand its physical limits, the 4 valves, and the dynamic feedback that drives it. But for the applications we actually care about, web pages loading, files transferring, video streaming, the TCP pipe is just the foundation. It's the delivery truck, but it's not the warehouse or the recipient. To understand true end-to-end performance, we have to look at what happens above TCP. From the application's point of view, we must consider everything above TCP as well. The end-to-end performance between two applications is limited by the narrowest valve in the entire chain. This includes TCP and below, the network pipe we discussed. It includes the host system, the kernel, CPU, memory, and NIC performance on both ends. And it includes the application layer, the protocol itself, business logic, and critically, the speed at which the application can generate or consume data. So the final complete formula becomes: transfer rate is less than or equal to the minimum of TCP and network limits, host system limits, and application limits. If the upper layer can supply enough data, then the transmission capacity of the TCP pipe itself becomes the upper limit. But if the application can't generate data fast enough, TCP becomes hungry for data. The pipe is ready, but there's nothing to fill it with. The transport layer sits idle, not because of the network, but because of the application. All right, we've now briefly completed our introduction to the end-to-end path model. In this episode, we learned to see the network in layers. From the pure network path view, there's one bottleneck controlling flow, simplifying the complex path down to a single pipe. From the TCP end-to-end view, 4 valves determine the maximum possible bytes in flight, guided by the 5th factor, feedback signals. And from the application end-to-end view, performance depends on the narrowest link in the entire chain, including the host and the app itself. All right, that's all for today. Now the question is, if the network is just one pipe, what happens when we try to fill it? In the next episode, we'll push data into that pipe and watch it in action. I'm Tai Fung, and I'll see you in the next episode.